not all functions have inverses. For example, if I were to take the graph of this and call this f of x, this graph, this function, does not have an inverse, because if I were to swap the x's and the y's, or let's do it the other way, let's do this. Well, let's come over. We know that point's going to be the same. Well, you should note that I'm going to have the same y value for both of these x's. So what's going to happen is, if I were to try to graph this using either my reflection technique or going horizontally and then vertically, and then horizontally and then vertically, you're going to end up with something where you have a graph that does not pass the vertical line test. So you can tell from the graph of a function whether or not it's going to have an inverse by what we call the horizontal line test, where I take an infinite number of horizontal lines, and if it crosses the graph of the function more than once in any location, for example, it crosses it at 3 locations here, we can say that the function does not have an inverse. So in order for a function to have an inverse, it must pass what we call the horizontal line test. Okay, in Algebra 2, we told you that something that passes the horizontal line test was a 1, 2, 1 function. That means that each x produced exactly one y, which is the definition of a function, and that each y value was used once and only once. So let's talk about our standard quadratic function, y equals x squared. Or f of x equals x squared. And you should notice that it fails the horizontal line test. So there is no inverse function for the squaring function. Well, intuitively, you think that the square root function is the inverse to the squaring function. But the only way that that'll work is if I were to actually graph the inverse of this function, this is what you would get. You'd get 0, 1, and negative 1. And then I go over to 2. I would get 4 and negative 4. You should notice that what you get here in blue is not a function. It fails the vertical line test. So we have to have a way to actually think about the squaring function and the square root function being inverses of each other. And the way we do that is we restrict the domain of the squaring function to be x's greater than or equal to 0. So what I'm going to graph now is the restricted squaring function. Where the restricted squaring function, f of x, is equal to x squared, but I put a restriction on the x where x has to be greater than or equal to 0. So the graph of the restricted squaring function looks like this. And you should notice now that that does pass the horizontal line test. And if I were to graph its inverse, which is the square root function, it now passes the vertical line test. So I can take any function I want to, and I can restrict its domain in order to get it to be 1-to-1, and I can come up with, for example, on this first graph, if I were to restrict the domain between negative 1/2 and positive 2, this portion of the graph does pass the horizontal line test, and I can have an inverse that is the restricted f of x function in between here and here, and I could get an inverse. I could also, similarly, restrict the domain of my original function from 2 to infinity. That section of the graph passes the horizontal line test. We're going to see several examples throughout the rest of the year where I have to restrict domains of the original function in order to come up with what we think about is the inverse of a function. Next thing I'm going to graph is f of x. Actually, we're going to not write it that way. We're going to write x squared plus y squared equals 9. You should recognize that from Algebra 2 or the beginning of this year, that is the equation for a circle that has a center at 0, 0 and has a radius at 3. And you should notice that not only is that not a function, but it doesn't even have an inverse. Okay? So be careful when you're asked to, graph inverse functions and stuff like that. One, you actually have to have a function in order to graph its inverse. And two, in order for there to be an inverse to the function, the original function must pass the horizontal line test. If it doesn't pass the horizontal line test, we're going to restrict the domain. And if it doesn't pass the vertical line test to be a function, then we could come up with other ways to define this function. For example, I could restrict it such that y's is greater than or equal to 0, and that would give me this blue graph, which now has a function, but it still violates the horizontal line test, so it won't have a inverse. Well, if I want it to have an inverse, I can restrict the domain from here to here, and that domain would be x's greater than or equal to 0, which would leave me with just that portion of the circle, or a quarter of a circle, and then that would have an inverse function, which would just be a reflection across the identity function, and in this case it would be itself. Because the other way I said, hey, rotate it 90 degrees, well, that would give you this. Then reflect it across the y-axis, which would turn it back into that. So that restricted circle function, which is that quarter of the circle, is its own inverse.